Hello, I'm welcome to this presentation on the use of AirPark, our CFD tool which was developed in-house to help in the design process for car park ventilation systems. My name is David. I'm a CFD engineer here working at Woods, working in the car parks department, and I will be providing the training for you here today. So a quick overview of the aims of the session. Hopefully by the end, you'll know how to physically use the program, and you'll understand where to find it as well, and understand what the results produced by the program are showing you and how best to interpret them. Additionally, hopefully you'll come away with some best practice ideas of how best to use the tool in aid of designing car park ventilation systems and the design process that you use. So what is AirPark? AirPark is a browser-based CFD tool built specifically for use in simulating car parks, with the aim of being simple to use and being able to turn around results much more quickly than with your standard CFD software. It's been designed in-house as a non-mesh independent CFD, which basically means that it's been more focused towards speed and the turnaround time of results than 100% accuracy in terms of the results you're getting. The results you're getting will still be very accurate, but they're not. But they're more intended to be used as a representation of what's happening in the car park, as opposed to being a validation of this is what's happening. Share this with the regulators to prove that this is correct and what will be happening in the car park. The program allows you to quickly build out a model of your car park, allowing you to trace around architectural drawings and using drag and drop to build out the car park and its features within the program much more quickly than with standard CAD software. Using this model, you're then able to simulate the movement of air within the car park, allowing you to understand the behavior of the airflow and providing valuable insight into system performance, helping you to design and optimize your ventilation system. It does this in the time frame of minutes, considerably faster than with the normal CFD study, meaning that can be used and implemented into your workflow at the design stage because of the quick turnaround results, ultimately meaning you can use it to produce hopefully a much better ventilation system than you would do it otherwise, just by looking at your drawings and thinking where to put the jet fans to create a good system. These results can also be taken and used as part of a proposal to clients in preliminary design documents, providing them with helpful visuals at a crucial stage in the process of a project, which could be key in helping to win the project versus what competitors may be offering. Also, by using this, hopefully you'll be able to reduce the number of jet fans relative to the competitors and giving you another competitive advantage in another way. Lastly, the program has inbuilt collaboration functionality, allowing you to share projects with other colleagues and quickly get second opinions on things, allowing multiple viewpoints into the same project, potentially being able to see things in different ways and overall, hopefully, being able to come to a better solution. This functionality extends to us here at Woods in the CFD department, allowing you to get expert help and advice should it be needed, and also allowing us to check through your projects, make sure everything's set up correctly, working, and there's no obvious mistakes before it's then put through the solver. So you know what's coming out at the other end is appropriate for what you're trying to model. However, there are a number of other limitations in the current version of AirPark. Simulations can only be conducted currently for pollution mode or everyday ventilation. However, as the general behavior of the airflow will generally remain the same between pollution and emergency modes, the insight provided by the program will still be accurate and useful for helping design the system to function in emergency situations as well as in general everyday ventilation. The way the program creates the model means that it's only possible to model single floors at any one time, This means that additional considerations have to be made in the design of the system and in the setup of the boundary conditions in order to most accurately represent the intended car park. This means that again, you have to make additional considerations, taking into account various factors, such as how the air you might have lower floors in the system, and how the air may be wanting to be drawn down onto these lower basement floors, and putting in boundary conditions additional to the ones on your current floor, on the floor you're modelling, sorry, in order to account for this and whatnot. Lastly, ceiling obstructions are not currently able to be modelled. So where you have ceiling height changes or beams or ducts located at high level in the car park, for example, you will have to make approximations and make allowances for them, understanding that while it may suggest that a single jet fan could handle a certain length of the car park and ventilate it effectively, due to these missing obstructions, in reality, they'll be sapping the energy from the airflow, meaning that it might only effectively be able to cover half of that distance that is actually shown in the results of your simulation. So where is AirPark? AirPark is, as I said, a browser-based CFD tool. It's found online at this web address here, airpark.flatgroup.com. Or alternatively, if you're already familiar with Fan Selector, there is a way of accessing it through Fan Selector. It is a shortcut in the sidebar. The program uses the same Flat Group account system as Fan Selector. So when you load up AirPark and come onto this screen, there'll be a login button in the top right corner. If you already have a Flat Group account, you can log in using that, or if you don't, you can easily create your own account specifically to use this program. Because this is a Teams meeting, thankfully, I have access to the internet, so I'll be able to give you a live demonstration of using AirPark right here. So, switching over to the internet version here. This is, as I said, this is the screen you'll see when you load up the program. At the top, you have your login. You have your login button here, and then here you have different options for you to use in the program. Clicking onto projects will take a while to load up because I have quite a few projects in my save system. Clicking on projects will load up this screen. Here you can see all your past projects that you've worked on, allowing you to go back and open them up and start working them on again. You can flick through the various, it shows 10 different projects per screen, and you can flick through the various different tabs using this bar at the bottom here to navigate through the system. You have a number of different options here. You can either click on a previous project to open it up and continue working on it, or you have a number of actions you can take. You can either copy the project, allowing you to create a clone of it, allowing you to save a draft almost, so that you can then keep your previous results whilst working on a different version of the same project, using a different ventilation design, allowing you to compare and contrast and giving you other options in terms of trying to create a better system. You can also delete the project to tidy up your inbox, which looking at this, I probably should do a bit more, to be honest with you. And there's an option to share the project, as I mentioned. If you click on this, it comes up with this box. Just enter the email address of the person you want to share it with. It will then appear in said person's inbox, well, in projects list, sorry, as it does with yours. So giving you both access. When I say both, you can share with multiple people, giving you all access to the project to look into and make changes and work on it together. To create a new car park, you click here, new car park. Here it loads up the new car park screen. At the top here, you have a number of administrative type details for your car park. You need to insert a project name in order for the system to create it and save it. And these other information, well, these other boxes, they're not necessarily needed to fill in terms of creating the car park. However, they can be useful for logging things and administrative purposes. Down here, you have a few options for your car park settings. You have the option to change the number of floors in your car park. You can also add more floors later if you wish. And it also gives you the options to change the default ceiling height and the default available space of your fans across all your floors. Again, later on, when you're setting up the individual floors, you can select the individual ceiling height and individual available space of fans for that specific floor. But doing so here, if they're all the same level, it just does it all at once for you. And if for some reason you'd want to use a system other than metric, you have the options here to change that as well. Moving further down, you have a few presets for ventilation requirements. Number of different countries here, depending on what market you're working in. Have Iceland here as well. Then alternatively, you can just click any and set up your own ventilation requirements as per how you want it to. Using Romania as an example, you'll see it instantly loads up the 300 for 2-hour high temperature regulations and the country standard over here, which, depending on whether it's for sprinklers or no sprinklers, is 300 meters cubed per hour per car parking space for normal mode, and either 600 or 900 meters cubed per hour parking space, depending on whether it's got sprinklers or no sprinklers, for example. So today, for our example, we'll just create our own using any. The default setting is for 6 and 10 air changes per hour, as that's generally the international standard we tend to see most often. So once you've done all this, click Create Car Park in the top corner, and it will create your project for you. So we only selected one floor, so it's only created one floor for us. Clicking into that floor, it comes up with this floor details screen. Here, as I mentioned before, where you can select the dimensions of the individual floor for the height and the available space of fans. And it gives you a few bits of information regarding the floor summary down here, which will pop up once you've created the floor in the floor designer. Clicking on this image here will open up the floor designer itself. And I'll bring you to this screen. Here you have the option of a few different things. Either top one to freehand draw the car park on a blank piece of paper. Or alternatively, you can either import an image or PDF file of the car park to trace around, or import a CAD file, a DWG, and specifically choose what layers you want to then import into the software. And then again, once it's imported, allowing you to trace around the car park to get an accurate representation of the car park you're trying to model. So for our example here today, we'll be importing a DWG file. So here's where you can select which individual layers you want to import. For the purposes of this, we're just going to select all of them. Then once it's recognized it and loaded into the system, click Draw Floor. And here is our car park. So a few basic controls within the floor designer, firstly to begin with. You might intuitively expect that moving the screen around like this would be to hold the mouse wheel and drag it. However, that isn't the case. Instead, to drag the screen around, it's a right mouse button. Left mouse button is your standard to click things and manipulate things, and then your mouse wheel is to zoom in and out like so. So we've got our car park in the floored. We've got our background traced around in the floored designer now. So first thing to do is to draw the floor boundary. You start by clicking at a point around the edge of the car park where you want to start the boundary. Then clicking at each point again where you want to change the direction of the boundary, drawing around the outline of the car park with everything inside this boundary then being included as part of the model. The idea behind this is to get a representative model representing what the flow physics and the airflow behavior will be inside your car park. The idea isn't necessarily to get 100% accurate simulation. So as such, you want to be getting the outlines and your features built into the model correctly, but it's not critically important that you get everything 100% exact relative to the background that you're tracing around. So then once you've drawn in your outline, good idea is always to lock it. That way, should you get confused with the controls, it won't drag your outline around the page and mess your car park up. Like for example, if I was to unlock it now and I was to forget that right mouse button is the drag and intuitively go for hold down the mouse wheel, as you can see, it drags everything around and messes things up. I've done that plenty of times using this throughout my time working on this. So always a good idea, lock it. It saves you problems in the long run. So once you've got your outline in, the next thing you need to do is scale your outline. The program just imports the background which you trace around just as an image without any scaling or any references or anything like that. So once you've done that, once you've got your outline, the first thing you need to do is to scale it. The way I like to do this is by using a car parking space. The way this works is the same with the outline. You click at one point, click at another point to set a certain length, and then come up with this box, and you'll define how long that length is. I like to do it with the length of the car parking space because it's pretty much always 5 meters. With this car park here, I've measured it beforehand. It is exactly 5 meters. So that's what we'll use. But generally speaking, that's the best way I find to scale the model. So then once we've got that, we've got our outline complete. The next thing we need to do is to build out the features within the car park. To do this, we have a number of tools here on the right-hand side to help us. We've got blocks, which are used to build in the various support columns within the car park. Columns create round pillars, like so, and change the diameter like that, using the menu that pops up. To delete objects, right-click on them and just click delete on the menu that pops up. Additionally, you also have square pillars, like so. And again, same system, menu pops up, select your dimensions that you want to use, and then click on the screen where you want to place your objects. Polygons are used for more complex shapes within the car park, most often used for things like internal rooms where you've got stair cores, for example. Works on the same system as the outline. So you just click, and wherever the boundary changes, and then click on the original starting point to close the polygon off and create it. Walls, create walls, work in the same way as that. Just click, start it, click to end it, and then once you've created what you want to create, right click to exit out of it and then create the feature. With walls, you can also create slightly more complex walls. And to do that, you just continue the wall, continue clicking elsewhere, and it will create that for you. Again, right-clicking to exit out of it and create the feature at the end. Then, in addition to these obstructions, you also have our boundary conditions. Inlets are used to insert mechanical supply points into your car park. They can be imported and inserted onto walls or onto ceilings, as well as setting up the settings before placing it. Once you have placed your object, you can then click onto it and change it individually rather than having to do it each time before you click it and drag and drop it into the system. As you can see, a number of options here regarding the sizing and dimensions of your inlets. Also, you have tool to rotate them as well. For wall inlets, it's the same, except you also have the option to change the floor offset of the inlet as well as the other options. With the airflow, you can using the system will try and the program will try and automatically create duties for you based on your ventilation settings you set up in that first page with all the presets. However, you can override this and insert whatever duties you particularly want for that, for the boundary condition as well. Outlets work the same as the inlets, except rather than being for mechanical supply points, they're for mechanical extract points. Exactly the same. Wall outlets, ceiling outlets. Exactly the same process, except different color and for air going out of the car park rather than coming into it. And then environmentals. These boundary conditions are for natural supply points or for where you have natural openings into the car park, like, for example, an access ramp. Again, these work. They have options for ceiling and wall. There are slightly reduced options, obviously, because there's no duties associated with these. But one thing important to note is that you always have to have at least one environmental boundary condition in your model in order to get the solver to calculate it. And the reason for this is the solver works by solving the system relative to the environment, relative to environmental conditions, standard atmospheric conditions. So in order to give the system that reference point and where it is in the overall car park, you have to insert at least one environmental condition to get it to register that and get the solver to run and solve your project for you. So if I'm quickly building out our model here for you. Again, as I said, the features don't have to be 100% accurate. The idea is that you're representing what's happening in the car park. So you want them to be as accurate as you can get them, but you don't have to painstakingly size them to be 100% accurate. You can just get them to be roughly right and then plot them in. Speeds up the process. When you select your details for your objects, it will then save those details, and you can then just continually drag and drop for the object shape you've put in based on these details here. So that's all the pillars now put into our car park. Now I've already done one of the internal rooms. There's only one other in this car park. And now onto our boundary conditions. In this car park, we have 2 extract points, one here, and no mechanical supply points. The only supply point being the natural supply incoming from the ramp here. Now, as I said before, the system will try and automatically populate duties for your supply and extract points. However, I'm going to override them for the purposes of this demonstration. Also, it helpfully gives you an idea of what the velocity will be for your louvers that you've put in based on the duties and things that have been inserted into the system based on the size of the louvers as well. So now we have our completed car park. What you do, if you don't particularly have any idea of what kind of system you want, what kind of design, sorry, you'd want to implement for this car park, this is where you could submit it for CFD, and it will just simulate it without any jet fans in, give you an idea of the overall bulk airflow without any jet fans in, for which you can use to then create a first draft of your system to give you an idea of how to start with your design. However, if you already have an idea of what you want to do, or you're working from a consultant's drawing or whatever, you then add your products using this button here. Gives you a list of all the jet fans available, different operating frequencies, different variations of the models using deflectors, guards, different accessories, terminal box isolator. It also gives you the option to use reversible fans as well as unidirectional ones. To insert your jet fans, just click on the model and type you want to use, and then drag and drop, as with the pillars. Once you've put your jet fans in, click on it, opens up this menu, gives you a number of options to select for your jet fan to specify what you want. Good idea, because of how the solver currently operates on the live version. It solves the system at the height. Sorry, the results it produce are taken at the height of the jet fans. So if your distance from the ceiling is 0, it will take the results at literally on the ceiling, which can create a number of artifacts which are non-realistic. So by the presence of the cut plane being on the ceiling, so by dropping it down slightly, you'll remove that and get a more accurate set of results for what you're trying to simulate. Also gives you the option to rotate the jet fans. You can either do it by this tool on the screen or by manually inserting a specific angle there. Additionally, with the distance from the ceiling, can be useful for imagining in the car park where you might have beams and you want to mount them below the beams, for example. You can put that in there to model that as well. So then once you have your car park and what you want to simulate, you come up here and press the submit button. Now on my screen, I don't have the submit button. I just have full CFD and CFD with no fans. When your screen, you'll have the submit button. What will happen when you press that submit button is that an email will be sent, a notification and an email will be sent to us here in the car parks department, and we will then get a notification saying there's a project been submitted, it needs checking. We will then load up AirPark, access your project which you've submitted, and then check through it all, make sure it's all functionally working, functionally okay, make sure there's no obvious errors or anything obvious which will cause the system to fail or anything like that. Once we've checked it's all okay, we will then run the project for you, which will usually take, at most, depending on how big of a car park it is, at most an hour. Then if you check back later, you'll hopefully see your results in your project already and completed for you. So if we imagine that I've pressed full CFD here, the project is now simulating, and move back on over to the presentation. Here is what we might see once the simulation has been run on our car park with no jet fans present. The results here presented are in two separate images: age of air contours on the left and velocity contours on the right. These are taken as cut plots at the plane of the selected jet fan height you put in when putting in your jet fans into the system. The age of air contours give us an idea of how effective the system is at ventilating the different areas of the car park. It's measured in air changes per hour, with the colours corresponding to an estimation of how many times within an hour the air in a specific region will be changed. Blue areas represent areas of greater air changes per hour, and the redder orange areas represent areas where you're not getting as many air changes per hour, and the air in that area is going to be more stale and the area generally less well ventilated. The total air change rate in the car park is purely determined by the size of your extracts. The jet fans themselves, unless you're working on a hybrid system, will have no impact on the total extract rate. Therefore, the job of the jet fans is to improve the overall system performance by distributing this fresh supply air around the car park, ensuring that all areas you're getting greens and blues and better ventilation throughout the car park, with the idea to get rid of these worse oranger red areas to get an overall better system. The suitable air change rate for the project will be highly dependent on the market you're in and the extract duties that have been specified. Because, let's say, for example, in Romania again, the extract duties are, by the regulations, are less than what you'd get in the UK. What a result which would look good for a Romanian project may appear to be terrible based on your overall general view of things, particularly compared to, say, a UK project, as a saying, because of the lower extract rates, making the contours appear more yellowy, skewed more towards the yellowy orange side of things. However, because the total extract rate and the air changes per hour are limited by that lower extract rate dictated by the regulations, a good project will look worse than what you'd expect. On the right here, we have velocity contours. These give us an idea of the behaviour of the airflows within the car park. The plot shows us the velocity of the air in the different areas of the car park, with the slower regions appearing more dark blue and the faster regions appearing more towards the red end on a scale going through these lighter blue, greener areas, which you can see here. Using this, we can see where the air is flowing within the car park and at what speed, allowing us to visualize the overall flow patterns within the car park and thus identify regions of recirculation which could cause pollution to be retained within the car park or lead to smoke logging in an emergency situation, leading to an overall reduction of performance as the pollutants are retained and recirculated around the car park into areas where it may not necessarily have been there before, and just generally retaining it and not being directed towards the extract and extracted from the system. So, an overview of the situation within our car park. We have 2 extract points located in the middle, and we have a single natural supply point from the access ramp with no other supplementary mechanical supplies. We have a ceiling height of 3 meters, which is on the borderline if in terms of optimal performance between a 31 and 35 diameter jet fan for this situation. You have a flat ceiling with no obstructions present upon it as well. The fact that the extract points are located towards the centre of the car park makes the system a more challenging one, as we will have to direct the incoming fresh air around the car park first in order to ventilate all areas before directing it towards the extracts to be extracted. Ideally, we would have the extracts located up here in the top left corner of the car park. This would then allow us to blow the air directly across the car park, just simply ventilating all areas without any complicated layouts or an excessive number of jet fans. But because of how the architects have designed this car park, they're in the middle, which means we have to deal with it and come up with a system that will work with the geometry of the car park that has been given to us here. The height of the car park is the main determinant for the size of the jet fan to use. The jet fan having to generate a large enough flow that can affect the flow at floor level as well as ceiling level where the jet fans are located. If you've got a particularly high car park, let's say 5 meters high, and you're selecting the smallest jet fan available, that jet fan is not going to be able to fully ventilate effectively floor to ceiling height. So therefore meaning that you'd need to select larger jet fans in order to deal with larger height car parks. With these key points, we can now come up with a first concept for our overall layout for our jet fan system. And here it is. The key idea with this layout is to position the jet fans in the areas of weaker clearance rates. So as you can see here in the redder and more orange areas, the idea is that we'll blow out air from these regions, having the effect of also drawing in fresh air into these stale areas to replace the air that has been blown out, and then directing the fresh air which is drawn in around the car park so that it passes all around the edge, ventilating all areas effectively before then being directed down into the area of the extract collected and extracted from the car park. As mentioned, this is 3 meters high, and so here for the initial layout, I've gone with the 35 JTV jet fans due to said height. And, oh, oops. Sorry about that. The results of our first layout. Has it worked? Well, it has sort of worked. The stale air has been removed from these outer regions, outer more enclosed regions, and this is by factor of the air being drawn into here, it has created a more well ventilated areas throughout the car park here in these areas which were previously quite stale and stagnant. The velocity contours then showing the path the air is taking through the car park, blowing round and down and into this extract region here. However, despite this generally decent distribution of air, you can see here, the jet fans are interacting with each other, generating a strong region of recirculation here, which could, as I mentioned before, cause pollutants to be retained within the car park, weakening system performance and potentially leading to smoke logging in an emergency situation. This is something which needs fixing, so we'll need to create a new system to improve upon this. So what we have done here is we have replaced the 35 JTV jet fans with the 31s for this top fan and this bottom fan here. The reduced mass flow from these fans has then reduced the flows around this recirculation region, as a result, reducing the strength of the recirculation and reducing the overall impact that it will have on the system. However, as a result of this, the bottom fan is now no longer capable of influencing the airflow quite as it did before, because it's not as powerful and therefore not producing as much of a mass flow rate through the car park. The result of this is a portion of the supply air is now short-circuiting from the ramp directly to this first extract here, cutting out the rest of the car park, meaning that the overall distribution of air within the car park isn't very good, and it could be significantly improved to get a much more effective system overall. By removing this short-circuiting down here, we can improve the overall distribution and generally get a more efficient system to be used for the jet fan layout. So, adding this extra fan here, the idea is to blow the air up this first channel, directing it away from this extract here, thus reducing the short-circuiting. Has it worked? Well, yes, as you can see, some air is being blown up here, and the scale of the short-circuiting has been reduced. And generally, as a result of that, you can see the rest of the car park has become slightly more green and slightly less yellow. But as you can see, there is still some short-circuiting present. So it might be a good idea to try again to further reduce this, to further improve the air distribution within the car park. By repositioning this bottom fan here, we are able to direct more air up that same first channel as we have tried to do with this jet fan here. By doing this, as you can see here, we've eliminated the short-circuiting. The angled fan almost also acts as a wall, directing and forcing the fresh air from the supply ramp to go up this first channel, while simultaneously blocking the air from around this other side that's been directed around the car park, from then coming back into this region here and going back round again. Instead, almost trapping it here to be collected by the extracts and preventing any kind of recirculation within the car park. As a result of this, more areas in the car park have turned further green, with this region here even starting to turn blue, showing greater air changes in this region and generally showing a better air distribution throughout the car park and a better system. However, because this jet fan here is now angled in this direction, it's no longer ventilating this middle part of the car park. So we're starting to see an area of yellow return in this middle section. So to deal with this, what we might need to do is to try and increase the velocity and the flow through here to better ventilate this region, to remove this slightly more stale area of the car park compared to the rest of the system. So what we've done here is we've replaced the 35 JTV fan with the 40 JTV fan. By doing this, we created a larger flow through here, greater velocity, allowing us to more effectively ventilate this region here, and thus blowing the air through here and getting rid of that slightly more stale region. As a result of this, well, normally we wouldn't use a 40 JTV fan for the car park of this size, sorry. But it's all about selecting the right fans for the right situation. The guidelines for optimal heights are just that, guidelines. It's important to take every car park as a separate entity in and of itself and adapt your system to best fit what car park you're faced with to create the best system possible. So now we have a system which works. We've got good distribution throughout the entire car park with no real areas of yellow or orange, and also showing no problematic airflow structures within the car park, no major areas of recirculation and no major short circuiting present at all. But in the process of doing that, we've increased the number of jet fans used in the system. So is it possible to reduce the jet fan quantity whilst maintaining the effectiveness of the overall system to create a more appealing proposal from a commercial standpoint? Well, here, what we've done, we've removed this bottom jet fan. And what this has done, it has overall not had a significant effect on the air distribution, only really turning these areas surrounding the supply ramp and the entrance area into the car park more green and less blue. Generally maintaining the performance of the system despite the lack of this jet fan, creating what will generally be considered a better system as a result. However, because we've lost this additional force created by this jet fan, we have returned some degree of recirculation, this fresh air being collected immediately by this extract point once more. So once again, we need to make changes to this to avoid this from happening, to return the performance level to what it was before we removed this jet fan. So what I've done here is I've once again repositioned and re-angled this bottom jet fan, angling it more across the car park, away from the extract point to more push the air towards this side and allow then this larger jet fan, now that we've put it into the car park, to then collect the air which is in this region and draw it to it and then blow it out again. By doing this, we've recreated this wall. Well, it's not really a wall, but it's an air wall in the car park, separating the two sides, preventing the supply air from getting over here, and then preventing the air which has been directed around the car park to ventilate it from escaping and recirculating, allowing it to be collected by the extracts here. So once again, we now have a functional, well-performing system, largely free from problematic airflow structures. But can we push this system further? Can we further reduce the jet fan quantity to create an even more appealing proposal? Yes, we can. The air in the top left corner is naturally drawn down and around to the extracts in the middle. Therefore, the jet fan up here is essentially redundant in terms of the effect it's having on the general airflow within the car park. So we can remove that jet fan and not have any material change shown to the system here. However, would I propose this system in an actual proposal? No, I would not. Within any CFD analysis, there is and will always be some degree of uncertainty. As mentioned before, with AirPark, the program has been more focused towards speed of returning of results rather than 100% accuracy. It is still accurate, and it does give a good representation of what the air is doing within the car park. However, it has been favoured speed so that it can be used in the design stage and give a good turnaround time of the results, so it can be used as an effective tool. Additionally, the results shown are only taken at the height of the jet fans. We do not know what is happening at the lower levels in the car park. The upshot of all this is that there is some degree of uncertainty in the results, and there is a chance that once the order has been won and a full CFD report has been commissioned, the system may not perform quite as expected as shown here. It is for this reason, it is always a good idea to leave some redundancy present in the system, so that if this does happen, there is room to play around with your jet fan layout in order to fix any issues that may arise and shown in the full CFD report, which you may not be expecting based on what you see in AirPark. By proposing the 3-fan system over the 2-fan system, you're able to do just that and avoid any issues which may pop up. Generally speaking, a good way to judge this, whether you're going to get issues or not in the future, is by instinct. If what you're seeing, you're generally thinking, you generally get the impression the system results, the air change rates and the velocity vectors appear too good to be true based on your extract points and your layout and what your general experience tells you, then generally speaking, it is probably going to be too good to be true. And therefore, it's probably going to be a good idea to add in an extra jet fan to give you that redundancy to deal with, as I said, any issues that may pop up. So a few key points to take away from this optimization process and procedure. Jet fans can be used to suck as well as blow. Generally speaking, the general idea with a jet fan is that it blows air out the back of it to ventilate the region behind it and direct air to where you want it to go. However, as a byproduct of that, it also has to draw air into the area where the jet fan is in order to replace the air it has blown out. As a result of that, by placing jet fans in regions of more stale air, it will naturally draw fresher supply air into that region, providing a good way of ventilating those more enclosed areas where the air is more stale and may not otherwise be able to get such a strong supply of supply air to the region. It's a good idea to position jet fans to work with the airflows already in the car park. I mean, we weren't able to do that so much with this in this example because of the relative positions of the extract points relative to the supply ramp. However, as I mentioned at the start when talking about the ideal extract point positioning, what we would have done would have been to just generally blow the air across the car park from one side to the other, using the natural flow of air from the access ramp towards the extract points, in order to just generally create a system that requires less jet fans and is therefore more simple, more cost effective, and a better overall solution. When you're positioning jet fans that work against the flow, you're always going to have to create more impulse, more power into the system, more energy. So you will require large jet fans and more of them to do this, which will increase system cost and complexity. Bigger fans are not always better, as well as more fans not always being better. By using bigger fans and by using more fans, you're increasing the general mass flow through the system. And if your mass flow through your system is greater than what the extracts are capable of extracting, you're going to create a certain excess mass flow, which will not be able to be extracted by the extract fans, which will then have to be recirculated back around into the car park, meaning that the car park will retain some pollution and some contaminants within it, despite the system operating as intended. So counterintuitively to some people, oftentimes by reducing the number of jet fans you're using, you're able to reduce this mass flow and then allow all the air that you're moving around the car park with your jet fans to be extracted first time round by the extract fans, therefore preventing said recirculation and preventing any issues with smoke clogging or pollution retention within the car park. As I mentioned, redundancy. Then, as I mentioned before, redundancy. Sometimes you will produce a system which looks too good to be true. If it does look too good to be true, it is likely to be too good to be true. Therefore, in said situation, it's a good idea. Make sure you design the system with some redundancy in mind, so that if it does in fact turn out too good to be true when you win the order, when the full CFD report is commissioned, you have room to play with your jet fans, with your system, to adapt to this and create a system which will function even if it hasn't functioned quite as you expected first time around. Sorry. And then lastly, it's a case-by-case basis. Every car park is different. While it's a good idea to generally have implement these design philosophies as you see fit. Implementing them in the same way every time will not produce the ideal system. It's important to look at the geometry of the car park, various locations of the different supply and extract points, the obstructions within the car park, to best create your system specifically for that car park, to best ventilate it and create a good air distribution within it to minimize whilst minimizing the total jet fans used, to create the most effective system overall and the most appealing commercial proposal for your jet fan system. So thank you for listening to my presentation. That about wraps it up.